be building on our knowledge of exponents by looking at the multiplication properties of exponents. We'll begin with what you know. In the expression 3 squared times 3 to the 5th, we know that we have a base of 3, an exponent of 2, showing us that 3 squared is equal to 3 times 3. These are both factors, and we're multiplying it times 3 to the 5th. 3 to the 5th will be 3 times 3 times 3 times 3 times 3. The base 3, it appears as a factor 5 times. When we multiply 3 squared times 3 to the 5th, therefore, our answer is 3 to the 7th because we have a total of 7 factors. The multiplication property of exponents that tells us that we can do this is you can add the exponents. Written algebraically, we have x to the n plus x to the m, excuse me, that would be times, we're multiplying, times x to the m equals x to the n plus m. And that's what we're doing in the above example. We're adding 3 to the 2 plus 5, which equals 3 to the 7th. This is the rule. If you forget the rule, you can apply what you know about exponents and powers to find your answer and help you remember the rule. Similarly, if we have 2 to the 4th times 3 to the 4th times 2 to the negative 2 times 3 squared, we're going to match up the like bases. In this case, we have a base of 2 and a base of 3. And we're going to add the exponents for those like bases. Using the commutative property, therefore, we have 2 to the 4th times 2 to the negative 2 times 3 to the 4th times 3 squared. Now let's add the exponents. For the base 2, we have 4 plus negative 2 times 3 to the 4 plus 2. Adding the exponents, we get our evaluated answer, which is 2 squared times 3 to the 6th. We can evaluate this further by finding the answer to 2 squared and 3 to the 6th. But right now, we'll leave this as its prime factors, a product of its prime factors. Let's look at one involving variables. This example, as a variable for our base, n to the 3rd power times n to the negative 4 times n. We would have the same base for all 3 factors, so we'll simply add their exponents. That gives us n to the 3 plus negative 4 plus 1, because remember, n is equal to n to the 1st power. When we add these exponents together, 3 plus negative 4 is negative 1 plus 1 is 0, and we have n to the 0, which equals 1. And this expression factors to 1. Now let's look at the word problem that I have at the top of the page. Light from the sun travels at about 1.86 times 10 to the 5th miles per second. It takes about 15,000 seconds for the light to reach Neptune. Find the approximate distance from the sun to Neptune. Write your answer in scientific notation. Now, paying attention to our labels, we have miles over seconds. This is a unit rate. We're going to multiply this times 15,000 seconds. The first thing to notice is that your units will cancel, and your final answer will be given in miles, which makes sense because we're asked to find the distance. Now to multiply 1.86 times 10 to the 5th, times 15,000, we could write 1.86 times 10 to the fifth in standard form. However, it's easier to write both of them in scientific notation. We have 1.86 times 10 to the fifth times, we're going to write 15,000 in scientific notation. That means we're going to move the decimal point 4 spots to the left. So 15,000 equals 1.5 times 10 to the fourth. Now we are going to use the commutative property to multiply 1.86 and 1.5. And we're also going to multiply numbers that have the same base, 10 to the fifth and 10 to the fourth. Multiply 10 to the fifth times 10 to the fourth, we simply add our exponents. 5 plus 4 is 9, so this is 10 to the 9. Now let's multiply 1.86 times 1.5. And that equals 2.79. This gives us our answer in scientific notation, 2.79 times 10 to the 9 miles, which we could then write in standard form if we desired. And that's the distance from the sun to Neptune. Next, we're going to take a look at what happens when we raise a power to a power. This is our third set of examples. I'm going to start with the problem 5 squared to the fourth power. Using what we know about exponents and bases, the base in this problem is 5 squared. It appears as a factor of 4 times, so we could write this out and expand it to 5 squared times 5 squared times 5 squared times 5 squared. So as you see, the base is 5 squared. It appears 4 times. Now let's apply our rules for multiplying numbers that have the same base that are raised to a power. We know we add the exponents. So this becomes 5 to the 2 plus 2 plus 2 plus 2 power, which equals 5 to the 8th power. There's a rule for this also. The rule for this problem is when you have a power raised to a power, you multiply the exponents. So this becomes 5 to the 2 times 4, which is 5 to the 8th power. And as you see, the rule does save time. However, if you forget the rule, you can expand your problem and write it out using what you know about exponents. Written algebraically, we can say when we have a number such as x raised to the nth power and then to the m power, we simply multiply n times m to get our final answer. Another example on this level is 4 to the third power to the 0 power. Now those of you that are paying attention know anything raised to the 0 power is 1, and that is our final answer. If you forget, you can simply multiply 3 times 0 to get 0, and you get the same answer. 4 to the 0 power is 1. What happens when you have a variable raised to a power? Again, you simply multiply the exponents. So here we have x to the third to the negative fifth times x to the fourth. Let's start simplifying. X to the 3, x to the third power to the negative fifth power becomes x to the negative 15th power times x to the fourth. Now we're multiplying two powers that have the same base, so we add the exponents. We get x to the negative 15th plus 4, which equals x to the negative 11. Remember, when you raise a power to a power, you multiply. When you're multiplying two powers with the same base, you add the exponents. We can take this one more step. We know that a negative exponent tells us to write the reciprocal of that base to the positive power. So this becomes 1 over x to the 11th. We're going one more level. Here's our fourth level of examples. We have the product of two factors raised to a power. Let's see what happens when we expand this. In this particular case, our base is 2y. We know it appears as a factor 2 times, so we can write this out as 2y times 2y. Well, 2 times 2 is 4, and y times y is y squared, so we get the answer 2y squared. Looking at the algebraic rule for this example, when you have a number x times a number y raised to a power n, that means you're going to apply the exponent to each factor. So this becomes x to the n times y to the n. It's like distributing, but you're distributing your exponent. Let's try another one. Negative 2y to the third power. We're going to apply the exponent of 3 to the negative 2, and we're going to apply the exponent of 3 to the y. So that gives us negative 2 times negative 2 times negative 2, which is negative 8, times y to the third. And our final answer is negative 8y to the third. And our last example, x to the sixth times y to the negative 3 raised to the second power. We'll break this apart and rewrite it as x to the sixth squared times y to the negative 3 squared. We're applying that exponent of 2 to each of the factors inside parentheses. X to the sixth squared becomes x to the 12 times y to the negative 3 times 2 is negative 6. How do I write this in simplest form? You have to remember that y to the negative 6 becomes 1 over y to the 6. So we have x to the 12 times 1 over y to the 6, which when we multiply our fractions together becomes x to the 12 over y to the 6. And that's our answer.